Okay, so, in quantum mechanics, there are very few potentials which are exactly solvable. Okay. So in quantum mechanics, there are very few potentials for which the Schrödinger wave equation is integrable, okay? So, what do I mean by that? So if I look at the Schrödinger wave equation, it's just like we are looking at the spatial part, this is nothing but, d of psi squared dx squared is equal to, say, is a plus minus k squared of psi squared, right? Essentially, this is the one-dimensional Schrödinger equation. So inside k squared is hiding the potential energy v, right? Now v can be some complicated polynomial function of x. So when you try to solve this equation, you might have to do a very complicated integration of x, right? And we know that is integration you don't know whether you'll be able to do an integration or not. So therefore, it's never clear from the beginning whether or not, whether or not you'd be able to solve the Schrödinger equation exactly. Okay, I just noticed that there are some questions that I did notice in the chat box. And somebody's asking about random matrix theory. So maybe I can just say something about random matrix theory. So random matrix theory is actually a generalization of quantum mechanics. It's actually a quantum field theory. Okay. So it's a quantum field theory in how should I say, in 0 dimensions. Okay, it's a quantum field theory in 0 dimensions. So in other words, it's a quantum field theory where the observables are Hermitian matrices. So quantum mechanics can be thought of as quantum field theory in 0 space and 1 time dimension. This is quantum mechanics. But matrix theory is random matrix theory, or can be thought of as a quantum field theory in 0 dimensions, where the observables are general Hermitian matrices. Okay, they don't have to be. All you know about this theory is that it has a Lagrangian. Okay, it has a Lagrangian or Hamiltonian. The Lagrangian point of view is preferred because random matrix theory is formulated in terms of path integrals. And in path integrals, the Lagrangian is, so for example, is preferred. So it could be, the Lagrangian could be, say, some, half m squared plus, say, I don't know, g by m cubed plus, say, lambda by 4, say, m to the power fourth, right? And then you want to kind of understand, what are the, what are the dynamics of the matrices? If you think of these matrices, what are the eigenvalue distribution of these matrices? In terms of quantum field theory. So it's a very different. It's a different. I asked this while you were discussing values of the distribution. Okay, I see. Okay. All right. So
is this randomness related to the random distribution of the coefficients when psi is measured? I mean, 100 copies of psi is measured.
not in an obvious way. I didn't think so. Yeah, it's a. I mean, they're kind of related, but not in an obvious way. Here, specifying, say, L gives you the distribution for your eigenvalue distribution. So if all these terms were not there, then it would be a Gaussian distribution, right?
Okay, sir, got it.
Okay, so all right. Okay, let's come back to what we were discussing, and what I wanted to discuss next is the idea that we cannot exactly solve all the Schrodinger equations, right? But what we can do is that we can develop some intuition about how to solve Schrodinger equation, okay? So I want to, how many classes do we have left? So we have one class day after tomorrow, and then we have, do we have like 5 classes left, or?
So when is the final?
Well, I mean, the final week is the 7th of, I think it ends on the 7th of, I'm just trying to measure because, I want to make sure that we do a good discussion on the harmonic oscillator. Okay, so.
With the tutorial, we have 5 classes.
The tutorial is not really a class; it's more of a problem-solving session. So we have essentially 4 classes, right?
Yes, sir.
Okay, that should be enough. That should be enough, because I want to end this course with a treatment of the harmonic oscillator. Okay, because if you do a quantum mechanics course and you don't know what the harmonic oscillator is, then it's it's not good. Okay, all right. So so next, what I wanted to do is that I want to develop some intuition about the generic features of bound states. So without actually solving the equation, okay? So we want to develop intuition. So the next topic is, general remarks on bound states. Okay, so Schrodinger equation is d squared psi, say dx squared, and this is minus 2m. Energy minus v of x. Energy is the constant because we are thinking of an eigenvalue here. And divided by h bar squared psi of x. Okay. So, sometimes we can even like solve this equation exactly, but it's so mathematically complicated that it's not worth it, because as physicists, we value intuition over mathematical rigor, okay? So if you can understand something intuitively, that, when you have something mathematically exact, if you can plot it, blah, blah, then you should be able to have physical intuition. But if you have a formula which is so complicated that you can't really understand the physics, then it's not worth anything. Okay, so there are two types of solution, right? For this guy, E can be greater than V, and for which, we can write this equation as a second derivative of psi equal to minus k squared of psi, where k is a positive quantity given by 2m E minus V. Okay, so when does this happen? This happens, for example, if you have a potential, say like this, and your energy is like that. So in this region, E is greater than V. So in that region, we are solving this equation. But in this region, E is less than V. In this region, E is less than V. So in such regions, the energy is negative. So E is less than V. And Schrodinger equation becomes where K1 is 2m V minus E rather than E minus V. Okay. So in region 2, in region 1, solutions will be, solutions, will be sinusoidal, right? In region 2, solutions, will be exponentially decaying. Okay. So the constraint that we have is that, psi must be, continuous, and psi prime must also be continuous. Okay. So by this I mean that e to the power, it would be plus minus k1 of x. Okay. So let's look at how the curvature of the potential, affects the, the solution. Okay. Or the curvature of the hang on. Yeah. So let's look at region 1. So in region 1, we have d squared of psi, d of x squared, and this is k squared of psi, right? So the thing is that, what does this measure? This measures the curvature of psi, right? Because suppose that we have a psi, which is, say, it's going like this. Then if I take its first derivative, what do I get? Is that I get that its first derivative, so this is, say, psi. Its first derivative is going to be something like this. It's negative here and it's positive here, right? So it'll be like this, right? So it'll be psi prime. And if I take its second derivative, I get a positive number, right? I get something like this, right? Whereas if I had, so for negative curvature, so this is a, is this correct? Here, yeah, I think so, yeah. Okay, for the other case, the negative curvature, if I have a wave function, say like this, then, its derivative is going to be something like this, right? And then we'll have psi double prime will be something like this, right? Now, because there's a minus sign, so in region 1, our Schrodinger equation is d squared psi dx squared is minus of k squared of psi, and this is a positive quantity. So because of that, we know that the curvature of the wave function will be such that it will concave towards the x-axis, okay? So the curvature of the wave function will be such that toward the x-axis. Okay? So by the same logic, if I look at the wave function in region 2, then psi will concave away from the x-axis. So this is something we have already seen qualitatively in the ground state. So if I go to the ground state, you see that this is the region where we have this is region 1, and here the wave function is concaving towards the x-axis, right? And whereas over here, it's going away. If it could go beyond this point, it would actually, go like this. Okay, it's concaving away from the x-axis. Okay, and these are very powerful observations, which allows us to sketch the wave functions, qualitatively.